Hello, everybody. My name is Ulrich Kloit, and I would like to have a short presentation about some alignment-related topics targeting the tasking TriCore toolset to show some requirements you have to follow according to the EABI and some options the toolset offers for modifying the alignments for certain requirements. In example, to achieve unaligned structures when there should be any alignment gap prevented in a, let's say, naked data stream. So the session will consist out of, let's say 10 to 15 minutes introduction to alignment topics, and then the remaining time for a short hands-on to show the important files or the important details in the compiler-generated files like map files or SRC files you can look at to collect or to control the alignment settings the compiler did apply to your C source code. So starting with the alignment restrictions of the TriCore architecture, some limited information about the Infineon EABI, which is a specification from Infineon, some information about the alignment options the compiler supports, and finally the LSL linker script language supports, and the hands-on at the end. So what is this all about? Alignment is simply that the toolset or the CPU you are using has some restrictions, related to alignment, which means it is not possible to have a completely unaligned code or data execution because the CPU instructions do not permit this. And you need to be not necessarily, you don't need to be aware of that because the compiler takes care of this, but this is an explanation of the root cause of all this alignment topics. So there are instructions like core register access instructions, which require a word aligned access, and context store instructions, which require half word aligned access. So a word is 4 bytes, a half word is 2 bytes for the TriCore architecture. And other instructions like load or store word or double word instruction. A double word is 8 bytes. They require half word alignment, so you cannot use an odd address for one of these instructions. Then this will be acknowledged with a bus trap by the TriCore CPU. And instructions like swap or load, modify, store, they have word alignment requirements, and pointers must be word aligned. And about these topics, if you don't program in assembly language, you don't have to worry that much about it, because the compiler takes care of fulfilling this alignment requirements, which are related to certain instructions which cannot be applied on byte aligned address. So then you have either word or at least half word aligned addresses. Of course, it can be overruled if you use an integer pointer and you cast an odd address value into that pointer, then it's a user error. Then the compiler is forced to produce, or the CPU is forced to produce an unaligned access using a word access instruction, which will provoke a bus error. A quick look into the Infineon EABI. So what is the EABI? It's an embedded application binary interface. It's a specification from the compiler vendor, and it tells the from the silicon vendor here Infineon. It tells the compiler vendors what they need to apply in their toolchain for this architecture. So they have the goal is to have a similar environment for everywhere, but this is not not really achieved because there are some things which are not specified in the EABI, or it's depending on the EABI version you are using. So Infineon did improve the EABI spec more and more, so that means there are less issues which are not included in the spec. So then you have clearer defined behavior of the C compiler. On the other hand, the EABI is restrictive with regards to alignment. So an int type must be 4-byte aligned. And this is not necessary for the hardware. So it's possible to have half-word aligned int data types. So you will introduce unnecessary alignment gaps due to the EABI. So one thing is following the EABI is according to the spec of the silicon vendor. But on the other hand, it is possible to soften these requirements. So the tools do include EABI options or an EABI switch to allow to change some things. So one example is EABI requires treat double as float. EABI requires treat double as double. So double must be an 8-byte value. And when you want to use hardware FPU for single precision float, it might be that you would prefer to have less accuracy and want to use float values instead of a double value. When the tools offer a treat double as float option where no double does exist anymore, and for all floating operations a hardware FPU is used, which is boosting the performance, but it won't be compliant to the EABI anymore because this requires that a double is an 8-byte value. But it's up to your requirements also to verify which options you should use. And one important thing about the TriCore, the tasking TriCore tools is that due to the fact that the EABI standard did change, so Infineon did release new versions which included more details. There are some additional options included to the EABI option, and this means using an older TriCore tools version like popular 4.2 R2 and using the latest version 6.3 R1. When you use the EABI compliant option, you won't have the same code generation because there are additional sub options introduced for the EABI option which are not present in older versions, and they lead to a different behavior, in example with regards to the struct member access or 0-bit bit fields instruct. So there have been some changes in newer EABIs. Just be aware of that. So you should have a peek, or you can have a peek in the Infineon EABI spec, and you should know that the compiler supports this EABI options to enable or disable individual EABI features or requirements. Yeah, here are just some examples. So characters must be stored on byte boundaries, short integers, half-word aligned data types with a size of 4 bytes, which means an int or a float, and a long or a double. They must be 4-byte aligned. This is a requirement according to the EABI, but not a requirement according to the instructions CPU can generate. So an int access can access a half-word address instead of a word address. So this is just a limitation of the EABI. Similar with array alignment topics, where the alignment of the array is predefined by the EABI settings here, and depending on the members, on the member of the arrays, or for structures, it is also depending on the struct member. So a struct of bytes can have 2-byte alignment, but as soon as there is an int member within a struct, then you will have a 4-byte alignment because the alignment of an int is 4 bytes. Okay, so what is possible with a compiler? So if you need to follow all the EABI alignments, then you can't apply all the options the compiler offers with regards to modifying the EABI settings and this __ align keyword or pragma align as an alternative. But this is options the compiler supports, which allows you to change the alignment of an individual variable. And a new feature introduced in the latest version of the TriCore tools, which is 6.3 revision 1, is that the __ align is also applicable to individual struct members. So it's not only about the alignment of the complete struct, but you can have a complete individual alignment of the struct members within one structure. And yeah, an unaligned keyword has been introduced for pointers and also for structs. So using an unaligned struct means it can start on an odd address, which means every single struct member access must be a byte access, because otherwise, if you execute a word access, you cannot guarantee that the struct member is aligned on a word address, because it is completely unaligned according to this requirement then when the unaligned keyword is applied. And packed is similar to unaligned, so you can define a struct as unaligned, you can define a struct as packed. The unaligned keyword can also be applied to individual struct members, and packed is applied to the whole struct. Yeah, last point here before we start with the hands-on. The linker script language is also capable of applying alignment requirements to sections. The benefit here is you don't have to touch the C source code. So you can, you don't need to recompile the C source code, but you can simply modify the linker script language and add some group entries to change the alignment of sections. This does not include the alignment of individual struct members. So this can't be changed by the linker. Only the alignment of the struct itself can be modified, or let's say increased by the linker. So here's an example to change the alignment of all sections within one linker group. Here's a group definition. It selects a couple of VSS sections, which are non-initialized, far-accessed or far-addressed variables. And here, for the group definition, there is an ordered and a contiguous keyword plus a fill keyword, which means the sections must be ordered in their order of appearance here in the group. There may not be any other alien sections injected. So there will be alignment gap entries when there is an alignment gap introduced due to the locate requirements, and the align equal 32 entry means the every single section part of that group will have a 32 byte alignment. Yeah, some other requirement topics. So if only the first section shall be aligned, then you can use an entry like this. So there is a main group, there is one subgroup which has so the main group has an ordered keyword, so all following subgroups will be in order. And the first group has an align equals 64 entry, which ensures that the first section will get a 64 byte alignment, and all following sections don't have any align entry here. So they will have the default alignment and won't have the 64 byte alignment. The same can be achieved using this when there is one main group with the align equal 64 for 64 byte alignment for the first section. And then there is here a subgroup introduced where the alignment is changed. So by default, the subgroup inherits the alignment of the main group. So typically the subgroup would inherit the align entry of 64, but it's possible to overrule it. So you can apply align equal 0, which means the linker can apply the default alignment to all sections selected in this subgroup. Yeah, last example here. An output section is something special where you can define a section which includes a number of input sections. You can define a specific size for the output section. So here it is 1000 hexadecimal bytes. And yeah, then you can use select entries to add some sections to that output section. And here it is also possible if a specific alignment is required for all the input sections, then you can introduce a subgroup like here with align equal 8 for to enforce an 8-byte alignment of every section which is included by this select statement. Yeah, one information about more details about this topic. So you can visit the tasking support website or the TriCore and Aurix tools and support section, where a link to the application notes is included. And this allows you to access application notes. In example, one application note related to this alignment topics, another application note for linker tips and tricks, and many other application notes. There are also follow-up sections about other topics, like next week on Thursday, how to set up the startup behavior of tasking EDE, and 1 week later, stacks and stack size estimation. And you can join this sessions without any additional registration, because your login details you have received for this session will also be valid for the following sessions. Okay, and now I'm gonna switch to the hands-on. So here is a tasking Eclipse environment. And here is just a few C source code files with very reduced content. So what do I want to show here? The unalign keyword applied to a struct definition. So here it's for the complete struct. Here's a packed keyword, which is basically the same for the same purpose. So which means the struct itself is not aligned. So it can start on a byte address, and all members of the struct will all be not aligned. So the C compiler will be forced to execute byte accesses for this struct. And here is a normal struct definition where the C compiler can suppose or can rely on the fact that this int value is at least half word aligned. So if the EABI is compliance is enabled, then it must be word aligned. So it will be on a 4-byte address, and then the C compiler will issue a word access to load or store a value in this variable. Same issue for pointers. So if I'm using an unaligned pointer to an unsigned int value, when I'm reading the content of the pointer, then or writing, then the compiler is forced to execute byte instructions. So to write one int value, it means there are 4 byte instructions required instead of using one store word or load word instruction, which is much more efficient, of course, but you don't have any alignment requirements. So this pointer can also point to an odd address to load an int value from an odd address. Yeah, here basically are small functions which do write a value in to this unaligned or aligned structures. And yeah, when they are compiled, we can have a quick glance here at the generated code. So here is the access of the unaligned struct. So it's simply to write one int value, which is 4 bytes, into an unaligned struct, or into an int member of an unaligned struct. And you can notice the code generation is not really efficient. So it needs to use some extract instruction to extract the 8-byte value from the 4-byte int, and then use store byte instructions to store the first, the second, the third, and the fourth byte in that addresses. So highly inefficient, but sometimes it is required that you need this unaligned access for whatever purpose. One example would be there is a struct which is generated by an 8-bit controller, which does not suffer from any alignment restrictions like a 16 or 32-bit CPU does, and it sends a naked data stream via an I/O interface, and you need to cope with that data stream without any alignment gaps, and then you can do so by applying this unaligned keyword to the struct definition. It's the same story for the packed keyword usage, so you can even compare the generated code. It is exactly the same if the complete struct is defined using unaligned or if packed is used. And here is the efficient variant when you don't use unaligned struct members, but a normal struct access. So then it's simply one store word instruction here to store the data at the address of the struct member. So the instructions before load the struct start address, and yeah, then here two move instructions do load the value, and the store word stores the value at the struct address. Here is another example for the _ align keyword. So you can use this to specify an alignment in the C source code of data or a function. So here is an unsigned int data with 8-byte alignment, an unsigned int data with 16-byte alignment, and a function with 32-byte alignment. And when we look at the generated code, you can verify it by this .align entry. So the function has been defined with _ align 32. So here is an .align 32 entry, which tells the linker finally to align this test _ align function on a 32 byte aligned address. And for the data, you can check here the definitions. So here is the aligned 8 variable, which got the .align 8 entry here, and for the 16-byte aligned one, it's the same story with .align 16. So these entries the C compiler does generate when you use the _ align, force the linker to fulfill this alignment requirement. Yeah, last C example here for the struct members. So here we have one struct consisting out of one char and one int type. It's a normal struct, so no unaligned is used here or no packed is used for the struct definition. And the second struct is, so the first struct has the second member with _ align 16 requirement. And the second struct is a normal struct where there is a char and the int member, which only have the EABI required alignment, which means the char will start on an even address and the int will have word address, the int member. So there is a risk that there is a gap of 3 bytes between the char and the int member. And this is visible in the assembly code. So looking at where we go, here is member 1, member 2. Yeah, so here is the access of the struct member with the align 18 requirement. So you can see it loads the value of the struct itself, and then the offset is 16 bytes because the following member needs to have 16-byte alignment. One additional thing to note here, the EABI requires that the struct has an alignment of the alignment requirements of the biggest member of the struct. So an int member has 4-byte alignment according to the EABI, and then this struct has also an alignment of 4 bytes. And when you use the __ align keyword to change the alignment of a struct member, then also the alignment of the struct itself is impacted. So you can notice here there is a dot align 16 because of the __ align 16 specified in the for the single struct member. Okay, last but not least, linker LSL script language. How does it work? Here are simply 3 unsigned int variables defined, and here is the LSL file where I added some conditionals. So here is the first situation where all members should have a 32-byte alignment. And when we look at the map file content in the locate results section, here you can notice that this is applied. So the name of the group is my group, and all these sections with BSS LSL, starting with BSS.LSL_align, shall be located in DSPR0 RAM and shall have 32-byte alignment. And here we go. Here's the first variable, here's the second, here's the third. Here are the alignment protection sections, which indicate that there is an alignment gap introduced due to alignment constraint I specified in the LSL file. And here in the alignment column, it proves that the linker followed the alignments. So 20 hexadecimal is 32 decimal. So here is the 32-byte alignment of the 3 struct members. And when I change it to use this, so here I want only the first variable to be 64-byte aligned, and the remaining can have normal alignment. I need to build the application. And here is a new LSL file generated, so everything located again in DSPR0 memory. And here is the align start group, so which is the first group here. And it starts on address 7 times 0, which is the beginning of the DSPR2 memory, and the alignment is 40 hexadecimal, which is 64 decimal. And you can notice the alignment of the following variables is only 4-byte, because according to the EABI, an int type variable must have 4-byte alignment. So they are following this 64-byte aligned starting section with normal alignment. So this, maybe I can skip this because this is the same, but just a different syntax. So here, 2 subgroups were introduced in one main group, and here it's one main group and one subgroup, and the subgroup changes the alignment. So this will achieve the same locate result, but the last one is then maybe worth to have a look at because it is using an output section. So here is the section named aligned output section, and I'm gonna link the example. And all input sections shall have 8-byte alignment, which is defined using this group align equal 8. And when we look at the results, so the aligned output section is here. The requirement was 64-byte for the output section. The size for the output section was 1000 bytes hexadecimal, so specified here. And now we need to find out where are our subgroups, so the BSS LSL align. They don't show up here because they are input groups, and the locate result section only shows us the output groups, which means this aligned output section group is listed here. But further down, there is a section named combined sections. And here we can look at the details. So here is what ends up in this aligned output section. And there we can notice that the first variable is loaded with a size of 4 bytes, has offset 0. The second has offset 8. And the last one has offset 10 hexadecimal. So it's following the alignment requirement that all sections of this included in that output sections shall have an 8-byte requirement alignment. And I can also verify it using at the symbols section. So there was a symbol section sorted on name and sorted on address. And when I use the sorted on address section, so here's the first variable, here's the second one, here's the third one, and they follow this 8-byte alignment requirement. Okay, it took longer than expected, but nevertheless, I hope you do have a little bit of time left. So if you want to ask a question, you can use the chat box for this purpose. And I'm just looking whether there are questions listed. So there should be a Q&A feature. Yeah, I'm looking. Okay, there are some questions incoming. Yeah, practical question about practical applications for using alignment. One thing is, like I explained before, when you have a naked data stream where you need to get rid of alignment restrictions. So then you can use this unaligned to have a struct consisting out of char and int and short and whatever type data type members, and then there won't be any alignment gaps included. Increasing the alignment can have a benefit that the linker, that the C compiler can apply more efficient code. So then it might be possible to use double word copy instructions instead of word copy instructions when a struct is copied, but that's also depending on the overall struct size. So there are reasons for changing the alignment. One reason for function alignment is to have defined behavior of a function. So there is some not well documented feature in the TriCore CPU that it is depending on the alignment of jump labels, whether there is a good or a bad performance when the code is executed. So you can have jump labels in if-else conditions, an example in your C code. And if you apply the same alignment for all functions, let's say 8-byte alignment, then you have the guarantee that the behavior of the function itself won't change, so the timing behavior. Otherwise, it can happen that you change something somewhere else, which results in a small shift of the remaining code, and then the following functions might be shifted by 2 bytes, and then you have a different performance behavior all of a sudden, and without changing anything in the source code. So this is irritating, but that's real life behavior. I experienced it myself. So there it can be useful to think about a dedicated or fixed start address alignment of a function. So one other question, what is about a language extension named __far? This is explained in the TriCore user guide, and it's nothing really special. So __far means that, or tells C compiler that it needs to use far accesses for the variable which is defined using this keyword, which are less efficient than near accesses. So underscore underscore near is the opposite keyword, which tells the C compiler to use near accesses for the data. But for near data access, there is some architecture requirement or instruction requirement. They must be located in the first 16 kilobyte of a 256 megabyte segment. And if this cannot be fulfilled, this requirement, then it must be a far data access, and far data can be located everywhere. Yeah, a question about the link to the recorded webinar. Yeah, you will get a follow-up, which means you will have access or you will receive a URL where you can download or view the video of this webinar. We will also add the slides I've used, and I can also add the small Eclipse project I'm using. Be aware that this Eclipse project is not suitable for any older version. So it needs some small adjustment with regards to the struct member align keyword or feature, because only 6.3 does support individual struct member alignment. So older versions will complain about the underscore unaligned keyword, and also about the underscore packed keyword, and also about the underscore unaligned, or no, about the underscore aligned keyword for a struct member. So, but otherwise you can have a look at the example code and also the SRC file, and excluding this non-compliant issues with the packed and unaligned stuff, you can also build it with older versions of the tasking TriCore tools. Yeah, there is a question about time difference between far and near. That's what I mentioned already. So if you access a near variable, it needs 2 instructions. If you access a far variable or a far accessed data, then it takes 1 additional instruction. So there is a performance penalty when a far access is used. But keep in mind, you can't address the whole memory range using near accesses, so only the first 16 kilobyte of every 256 megabyte segment. So there is limited amount of near RAM and near ROM available to store variables and const data. A difference between line and packed. So there is basically, no, there is a question about the performance difference between align and packed. There is not really a performance difference. To cut a long story short, if you force the C compiler to use byte instructions where it is not needed, because you have used the underscore packed or the no align keywords, then it will lead to a significant worse code generation, because let's say for one int access, it needs 4 byte accesses instead of 1 word access. So you have some significant amount of additional assembly instructions which are required. Yeah, one question. Did I miss something? Yeah, another question about the advantage of alignment. That's what I mentioned before. So if looking at the jump label alignment, it might be beneficial to ensure that all functions have dedicated alignment using this LSL linker script language feature, because then you have a defined function execution behavior. When a function is shifted slightly in memory, but the content is the same, you will have a different timing behavior. This might not be critical if the function is not executed that often. But if it's a critical function which is called very often, then you will notice this in the overall performance of the application when the function start address is slightly shifted because of this TriCore CPU behavior that a jump label is best 8-byte addressed, and if you shift a function, then you shift also the labels included in that function or the jump labels, and then you will have a different performance. Yeah, I think this is all. Okay, yeah, well, then I would like to thank you for listening. And in the follow-up, you will receive the link as soon as the information is available. So you can view the presentation again and also have a look at the slides I created and the example I used during this presentation. Okay, thanks a lot. Take care. Goodbye.